Okay.
Ready? Probably, I think I wanted to mention this yesterday, but I forgot. Announcement. I think our first test is going to be, not this Wednesday, although technically I could do it for this Wednesday, but I'll do it for the following Wednesday. So that's going to be there are no like holidays during that day, right? I don't remember. But I think so. Wednesday next week coming is the 21st, and then the next one is the 20th. And it's going to cover everything up until what we cover this Friday. So that's when the first test is going to be. So it's going to be on Chapter 6 essentially, and the few parts of Chapter 5 that we did. So this would cover what we did in Chapter 5 and 6. I will post a review, so you'll know sort of have a guide to what you should be studying. That is something I wanted to get done this week, but I got the flu, so that didn't work out. And I don't really want to rush it, because I want to be able to rest if I feel like it, so I can make sure I'm better as soon as possible. And so, yeah, so I'll post a review, so I'll give you a list of problems that you can practice. I'll also probably just put like a mock test or something like that, and put the solutions up as well, so you can kind of practice with that as well. So yeah, that's something I wanted to mention. So that's going to be our first test. Yeah, so study for that. The second test is actually going to come a lot quicker than the first test, so you should be aware of that. So we've been here like over a month at this point. It's almost 2 months, but the first test is actually going to be a lot. The second test will actually come a lot quicker, and the third test maybe. Yes.
Will this be during recitation?
Yeah, but you'll get the full period for the test in the recitation, and of course you'll have partial credit and all that stuff. So you're supposed to write out your full answers. It won't be like a quiz. You write out your full answers. You explain all your steps, and yeah, I'll grade based on that. Today we're actually going to cover, I think it's 6.7. We're going to talk about hyperbolic trig functions. And these are, again, similar to when we were talking about inverse trig functions. A lot of things here are, we're really doing accessory work here, because things that might come up later on when we're doing integrals and stuff. And hyperbolic functions, they have a tendency to pop up in all sorts of places, so in future math classes you're going to see them just pop up all over the place, and your professors will probably expect you to know about them or have seen them before, so I figured we'd cover them. So that's what we're going to do now. So I'm pretty much going to tell you their definition. I can't really talk about where the name comes from, because hyperbolic can mean so many different things in math, honestly. It's almost a meaningless word. So these are hyperbolic trig functions. They're not actually trig functions at all, believe it or not. They're actually kind of messing around the exponential function, but they have relationships to each other that makes them behave like trig. So they have their own kind of Pythagorean identity, and they have their ratios are set up similar, and they're similar to have similar relationships like SOHCAHTOA and things like that. So that's why they're called hyperbolic trig functions, but they're not really trig functions at all. The main ones here are what we call hyperbolic sine and cosine. And the abbreviation is sinh and cosh. So that's SINH of x, right? So that's, we pronounce it sinh for some reason. And then cosh of x. So it's like a sine with an h on it, that's the hyperbolic sine, and then cosine with an h on it, and that's the hyperbolic cosine. These are the definitions. E to the x minus e to the minus x over 2. That's the definition of the sinh function. This is the definition of the cosh function. So they're very similar, except the cosh has a positive and the sinh has a negative. So these are our functions here. Right? And we define the others. So we have what's the tanh function, and that, you guessed it, is what we get if we take sinh and divide by cosh. We also have the hyperbolic secant, that's your 1 over cosh. We have your hyperbolic cosecant, that's your 1 over sine, sinh. We also have your hyperbolic cotangent, and that's 1 over tanh. Now, I think I also mentioned that the exponential function is a very important function in general in calculus, and that's something you probably are aware of at this point. And so really, these guys do become useful in a lot of other spheres. Complex analysis, for example, if you guys do that, you're going to see this a lot. And differential equations, they might come up. Multivariable, you'll see them pop up all over the place. So they're very important functions. Their graphs, look at the y equals sinh. And just like the sine function, this is also an odd graph. It looks kind of like a cube root. Difference is it's actually asymptotic to if you graph the line y equals 1/2 e to the x, this graph will be asymptotic to that as it's going off to infinity. And its tail is asymptotic to minus e to the minus x. Okay. So overall, the shape looks like a cubic, but it does have some behaviors that a cubic would not have. It will increase exponentially as you're going off to infinity. So eventually it'll increase faster than any cubic. So sinh, just like sine, is odd, i.e. you take the sinh of minus x, you get the negative of sinh x. And it's all little behaviors like this is why they're called hyperbolic trig functions. So the sine, the sinh is odd, the cosh is even. If you look at y equals cosh, that actually looks like, it's almost like an x squared plus 1. So its lowest point is 1. But again, it increases exponentially. So cosh here is even, i.e. take the cosh of negative x, it's just the original cosh of x. I have here we want to graph the graph of tangent, but I think we can skip that. This guy also has asymptotes to the exponential value. So if we that side would be 1/2 e to the x, and this side is 1/2 e to the minus x. Those are the asymptotes. So here are some identities. Look at if we take cosh squared and we subtract sinh squared. Well, that's what happened. It doesn't work well over here for some reason. So this here would be e to the x plus e to the minus x squared over 2 minus e to the x minus e to the minus x squared over 2.
Do we not square the twos?
Yes. We're squaring the whole thing. The over 2 is here. So this would become e to the 2x plus 2 plus e to the minus 2x all over 4 minus e to the 2x minus 2 plus e to the minus 2x all over 4. And so what would happen here is notice that we'd have e to the 2x minus an e to the 2x. Those guys are actually cancelled. E to the minus 2x minus an e to the minus 2x. Those guys are going to cancel. You're going to have a plus 2 minus a negative 2, so that just becomes a plus 4. And you combine the fraction, you get 4, you actually get 1. And so there's something similar to a Pythagorean identity happening here, but instead of a plus, it's a minus that will work. Cosh squared x minus sinh squared x is equal to 1. And this is something you'll appreciate more when we get to parametric curves, when we're looking at patterns to take advantage of the fact that, for example, you can somehow think of the equation of a circle, in terms of cosine and sine. And there's a natural connection between these graphs, right? There's going to be a natural connection between something like x squared minus y squared equals 1 and this graph. And so this guy is useful in situations where you kind of want to change the variable on a hyperbola as opposed to a circle, right? You'll also see applications there. But that you'll really see when we talk about parametric curves. I'll mention that a little bit. What else do we want to mention about these guys? Just write some of these down. They also have their own addition formulas. By the way, let's just actually piggyback off that one. This also means, for example, that 1 minus tangent squared is equal to secant. So again, this is usually a plus if it's regular trig functions, but it's a minus here. There are times when these guys give you minuses instead of pluses, and times where they give you pluses instead of minuses. There are the addition formulas that you can prove as well. And they actually don't change signs. So if you have sinh of x plus y plus or minus, the cosine does not change sign, so the cosh actually takes the same sign value, which is again a difference between them and trig functions. So they behave a lot like trig functions in many cases, but there are sometimes when they differ in the sign, so you have to kind of be careful with that. Those are some identities that might come up in your homework. So let's move on. So how about derivatives? Right. We can differentiate these because we can write them as exponentials, and we know how to differentiate exponentials. So let's look, for example, at the derivative of sinh. This just means it's the derivative of e to the x minus e to the minus x all over 2. This is just, well, the derivative of e to the x is just e to the x. The over 2 is just going to stay. And the derivative of minus e to the x is minus e to the minus x. So you just get e to the x plus e to the minus x over 2. You'll notice that that's cosh. i.e., if you take the derivative of sinh, the answer is cosh. Similarly, if you take the derivative of cosh, that will actually give you sinh. Not minus sinh. Yeah.
Quick question about the sinh x plus y addition formula.
Yeah.
Is that sinh y or sinh x? Or the other side.
These switch. It's just like the addition formula for sine and cosine.
Okay. Thanks.
So you have those guys are true. So these are very important to know. We'll come up with some other expressions that are important to know. We also have... Let's try to write down the chain rule versions here. Okay, so let's just write down the chain rule versions. Sinh of u u prime cosh. Cosh of u is going to be u prime sinh. We can take the derivative of the tanh. This u prime. Turns out that will actually be the secant squared, just like the derivative of tangent is secant squared. The derivative of tanh is hyperbolic secant squared. So if you actually go through your trig rules and compare these, you realize that they're very similar. how these functions relate to each other. It's kind of why they got the name hyperbolic trig functions. Because you make these definitions, you call one guy sinh, one guy cosh, and then you define the ratios the same way you split up the SOHCAHTOA before. And all these rules kind of fall in line with the rules that we have for trig functions. And they have similar addition formulas as trig functions. You know, the derivative of the sinh is the cosh. You know, there are a lot of these patterns. So there are some times when you want to take advantage of a pattern, and it will be nice to use a trig function, but maybe there's a sign off. And so what you'd use instead is a hyperbolic trig function. It's kind of because you're kind of looking at a hyperbola instead of a circle. I think that's where the name for this one came from. I'm going to jump to examples now. They also have inverses, by the way, and they're maybe let's actually do an example. Then we'll do some more examples. Let's find the derivative, the cosh inverse of x. So here what we do, set y equals to the cosh inverse of x. This means that the cosh of y is going to be x. This means. And now we're going to differentiate implicitly, of course. So this is going to be y prime times sinh y equals 1. So this means that your y prime is equal to 1 over sinh y. Still in the block. It's probably not what I wanted. So I want to rewrite this in terms of x. And I think we want to use one of those identities. was that thing with the squares? No. What do we have? We had cosh squared x
Sinh squared x
minus sinh squared x equals 1, right? So this means we can solve for the sinh squared here, because I want to get rid of that sinh. So let's actually try to find another identity here. So this is cos squared x.
It's 1 minus cosh squared x.
No, that's right.
No, I moved this over
Oh,
here
okay.
and then the 1 over here. And so here my sinh is just going to be the square root of cosh. And by the way, I'm not taking the we ignore the negative because of the restricted domain used to make cosh inverse work. Right, so you remember I gave you the graph of cosh, it was like this. You actually couldn't take the inverse of that, so we actually ignored the negative side to make the inverse. So we're only taking there are only positive numbers to worry about here. So we take the positive number here. So what we end up with is that here our y prime is 1 over the sinh of y, but I can actually rewrite that as this guy. It's going to be the radical of the cosh squared of y minus 1. Cosh of y, though, was actually just x. And so this ends up being 1 over the radical of x squared minus 1. And so also like inverse trig functions, when we start to take their derivatives, they give us expressions that don't have the trig functions in them at all. So notice that when you were doing if this wasn't a hyperbolic, it would be 1 minus x squared, and in this one we have the x squared minus 1. So it's all a matter of when something will be useful. So something I was mentioning, so example. Like, and again, we're really only dealing with these guys as accessories. They are just going to help us in the future to do other things. We can know that if I take the antiderivative of 1 over the radical of x squared minus 1, I can actually think of this as being cosh inverse, right? But if I have 1 over the radical of 1 minus x squared, there are actually two things I could think of this as, but I can actually think of it as just the regular sine inverse. So it's a matter of, if you have an expression that looks like this, where you want to integrate something and then there's a radical and x squared minus 1, you can use the hyperbolic trig function, whereas if it's 1 minus x squared, you can use a regular inverse trig function. So it's really just giving us more options to take advantage of patterns and figure out integrals in the long run.
Quick question. We don't have to worry about restricting the domain for the sinh x, correct? 'Cause
No.
it's-
Yeah, because it was already 1 to 1 and 1 to the other. But for the cosh to work, we had to restrict the domain. So we can figure out the derivative of the inverses like that. And this leads to a bunch of other formulas. know that the derivative of sinh inverse. Well, you can do a similar trick to this, using this same identity instead of solving for sinh, solve for the cosh, and then do a similar thing, and you can end up finding the derivative of sinh inverse. I think I'll give you the chain rule versions. And that one will actually be also a plus. The derivative, let me just recopy this one. You can have them all in one place. U prime over u squared minus 1, derivative tangent inverse. You might remember that the derivative of tangent inverse is 1 over 1 plus u squared. U prime over 1 plus u squared. Here's if you have a minus sign, you can use the hyperbolic tangent. Although there will be other ways to deal with this, but this is just, again, another option. So those you can know. Here are just some optional knowledge for you. And again, you will be able to see a lot of similarities here between these guys and their trig counterparts. I verbally mentioned this when I was doing inverse trig, but let me actually explicitly state it here. Integration is going to be a big part of this course. It's one of the important sets of things that we learn in Calc 2, how to integrate a lot more complicated kinds of things. So at this point it goes without saying that any time I give you rules about derivatives is just, you can think of it as an integral rule in the reverse. And we'd actually often want to think of it this way. One of the main things missing from your Calc 1 class is a lot of integration. Right? Integrals you kind of learn towards the end, and they only teach you integration by substitution. So Calc 2 is really getting your integration up to speed, but we have to teach you all these background things, because a lot of integration, by the fundamental theorem of calculus, you know that it's kind of reversing differentiation. So I have to tell you a lot of things from the backwards perspective, and it will help you learn things in the integration perspective. But yeah, so I just want to mention that. That being said, let's actually write out some examples, which we're definitely not going to complete all of them. We're going to just find y prime. are just sort of to get used to working with these functions. But to be honest, you're really not going to see the hyperbolic functions pay off in Calc 2. You'll really start to appreciate these guys in higher math classes. They become very useful later on. Let's just start. Okay, so y is equal to cosh of x squared. Y prime would be 2x times sinh
Oh, yeah.
b. Y is equal to x cubed minus 3 sinh. So y prime would be
X cubed minus 3 times 1 cosh x plus sinh x times 3x to the fourth.
3x squared.
Sorry.
Product rule. Tangent of ln to y prime.
1 over x times secant h squared natural of x.
Okay, remember that the derivative of ln is 1 over x. What about that one?
X. Just do like quotient rule.
Could do quotient rule.
Reverse it.
Bottom times derivative of the top.
C squared x minus tan hx over x squared.
Doesn't make sense, but let's do it. E.
times, C, or
Sinh.
yeah. So 10.
So that's actually 10. Alright, similar to that, if you take the derivative of ln of cosine, you actually get minus tangent. So that's very similar to an integration rule, a derivative rule, which comes then as integration rule. So that finishes the first batch here, and we'll stop there, and we'll do these guys, do these four, beginning of next class. So next class, we're going to learn about indeterminate forms and L'Hopital's rule. That's going to give us another way of finding some interesting limits, and then we'll actually do the chapter on integration, which is kind of the reason why I'm here. And I'll see you guys. Yeah.
Can you go over how you did that last time?
Because the derivative of ln of anything is the derivative of the things. Or you can think of 1 over u times u1. So here this is the u, so it's 1 over that times the derivative.
I forgot about the U sign over here.
Yeah.